Okay, so let's wait a bit.
So you give me the go ahead, I suppose.
Yeah, I would just wait. Like I see, like people are getting in, and I think you can see it as well, no?
Actually, no, no.
Oh, okay. Well, anyway, so wait, everyone was there.
Hi, Anton again. Hi, Paco.
Hello.
Hi, I'm Rob Sewell. We've spoken via email, but
Yeah.
not made properly.
It's great to meet you.
Nice to meet you as well. Everything set for the talk?
Yeah.
Very good. We've had a couple of hundred people connecting in each of these, so hopefully we get a good audience today as well.
Yeah, I think we could start because we're already live.
Okay, so let me start by...
So I will just introduce you quickly. So thanks everyone for coming again. This is really great pleasure to get Paco Guinea on the second session of today's talk. So Paco is actually working both at IMDEA in Madrid and at DIPC in San Sebastian in Basque Country. And is really a pioneer in 2D physics theory. And he also, for that, received a large number of awards, including this National Prize for Physics in Spain, and also the gold medal for Spanish Physical Society. And he and his group are working on this novel properties for a device made of graphene, electric and structural properties, two-dimensional superconductivity, and also optical and structural properties of 2D semiconductors. So today we'll hear about electronic structures and interaction in these narrow bands in stacks of 2D materials. And thanks again, Paco, for joining. And the floor is yours.
Thanks a lot to the organizers of this groundbreaking event, and thanks also to the very professional staff at ICFO who have made it possible. Okay, so let me start by the early beginning. I mean, experiments on twisted bilayer started already in this 2011, more or less, with Ivan, Andrei, and his group. But the whole thing, as you know, exploded 2 years ago with these famous by now experiments from MIT, from Pablo Jarillo-Herrero's group, and that's what I would like to talk about. I will start with some introduction. I'm a theorist, so I will have a theory view of what's going on, and then I will move on to the new stuff we are working on at Madrid and San Sebastian. First, let me tell you that part of the interest in twisted bilayers is because it connects very much with a very broad subject in condensed matter physics, which is the strongly correlated, the field of strongly correlated systems. Here I outline a few of them, and they all have a phase diagram which looks quite a lot like what Pablo found at MIT in a twisted graphene. There are magnetic insulating phases and superconducting phases. Typically, and in that respect, there is a difference with graphene. The phases with the highest critical temperatures are the insulating phases, and that suggested in early times in work on these topics that pairing is probably due to fluctuations of the order parameter in the insulating phase, and probably those things are well captured by variations of the Hubbard model. These are relatively recent experiments on twisted bilayers, and it's true that the more experiments become available, the more prevalent superconductivity is with respect to the insulating phases. So there are similarities and differences between strongly correlated systems and twisted graphene. And it's the same thing when you discuss, I mean, in twisted graphene, it's all about the magic angles and narrow bands and the magic angles. And there are also interesting differences when it comes to the narrow bands, because in all the strongly correlated systems, or in almost all strongly correlated systems, you have narrow bands, but the narrow bands arise partially because you have highly localized orbitals. That's especially the case in the heavy fermion compounds where you have rare earths with F orbitals, and partially because the excitations are strongly renormalized. They have to drag, I mean, the quasi-particles are strongly renormalized. They have to drag a kind of cloud of excitations, and that lowers their velocity and narrows the bands. And in that respect, now I'm going to move to twisted graphene. First of all, let me highlight these two groundbreaking papers where you can learn everything. Yes? Sorry, Frank, are you saying something? Okay, I'll go. Sorry, so these two groundbreaking papers, first a paper by the Portuguese, Brazilian, Singaporean team, and then and McDonald, they already laid out everything you needed to know about the band structure of twisted bilayers. However, these things were already pre-mentioned in tight banding calculations. People have noticed already that there were flat bands in twisted bilayers at very small angles, and I will discuss this particular model I'm very fond of because I was involved in its origin. Okay, let me, I suppose you're tired of seeing this picture. Let me just stop here. The only thing I want to remark, this looks like the famous moire you have in a twisted bilayer, but this is not a commensurate angle. So if you look to all the AA regions, AB regions, and all that shown in this figure, they are not the same, they are different. However, we theorists claim that this is not a crucial difference, and probably it isn't, but it means it's a bit annoying that there's no detailed study of why the band picture you obtain by assuming this is a perfect moire works so well. Okay, and this is where the complexity of the band structure of twisted graphene comes about. It is coming from the fact that the states in each graphene layer, they are not at the center of the Brillouin zone at the gamma point, but at the corners. And when you rotate the Brillouin zone, then you have three corners which are equivalent within each layer, but from the point of view of the other layer, they are not equivalent. And as a result, when one block wave from one layer passes to the other layer, tunnels in a quantum coherent way to the other layer, it passes as three different plane waves. And then that proliferates and proliferates, and that creates a relatively complex Hamiltonian. Another way of looking at this thing is by saying that you cross the bands of the two layers, you open gaps and create Van Hoff singularities where the two cones intersect each other, and then eventually you get very flat. But this is, in my opinion, a bit incomplete picture. A better picture was pointed out by Stricker and McDonald already. You just need, in order to capture the essentials of the first magic angle, four graphene block waves, and what happens is not that the electrons become very slow. They keep moving at high velocity, but what happens at low angles is that you hybridize electrons in both layers, moving basically at the same velocity, but in opposite direction. There is a significant counterflow, and that's why the total Fermi velocity is very small, and as a result, you have narrow bands. But it's not that it's not like in a typical strongly correlated system where the electrons are strongly localized in particular atomic orbitals. They're still moving along the layers. Only this counterflow implies that there's no net displacement, so to speak. And let me mention, you can simplify the model, switch off AA hoppings between layers, then you have something which looks like a non-abelian gauge system, and there the magic angles are really magical. I mean, you have completely flat bands, which do not disperse, and also, in addition, it was pointed out in this paper by the Harvard team, it has very nice connections with quantum Hall physics. And nevertheless, even at the magic angle, you can, as I will mention later, you can make the bands disperse if you add interactions. And let me also mention, because very recently a new paper on this chiral model, as it is now called, was posted showing a different way of explaining why these magic angles appear in the model. Okay, so these are the magic angles, and let me flash through you this picture. This is what is happening at a magic angle. The two bands cross each other completely. So you can define the magic angle a la Twisted-McDonald as the angle at which the Fermi velocity vanishes, but you can also define the magic angle as the point where at the gamma point, for instance, here the two bands cross. And so there are different definitions of the magic angle, but all of them amount to the same. You have a very flat band. And the only other thing I wanted to highlight is that when you pass the first magic angle, the situation becomes very complex. You have many Dirac points. For a time, many Dirac points proliferate. Van Hoff singularities also proliferate. It's a nice paper by Leon Baden et al. About this complexity. So the first magic angle is rather special. I mean, there are many magic angles, but probably the first one is unique. And so this is, in summary, what I wanted to know about what we know now about the electronic structure of the twisted graphene bilayer. As I said, the fact that the tunneling happens at the coordinates of the Brillouin zone is crucial. And let me also mention or repeat that the only energy scales you have are relatively large. And here, so far, I have not discussed any interactions. So the reason why you have a flat band is not exactly the same reason why you have flat bands in strongly correlated systems. Okay, these are some of our early calculations using a tight banding model, and this is some set of bands, and this is a blow up of the narrow band at the beginning. And the other thing which also distinguishes strongly, we'll go back to this, the electronic structure before you turn on interactions of a twisted bilayer. And the electronic structure of a strongly correlated system is that this is the Brillouin zone. Depending on where you are in the Brillouin zone, at gamma, at M, or at K, you have quite different electronic charge distributions. In a cuprate, for instance, the charge is mostly all the time in a d orbital in copper, and that's the end of the story. Or in a heavy fermion system, the charge is mostly in some f orbital in a rare earth. It was noticed by these people at the beginning of the twisted bilayer work. Okay, and this complexity of the bands and the wave functions, I mean, of course, when people studied before strongly correlated systems, they noticed that things were very local. Precisely, the flat bands imply local electronic properties, and the way to study a system where electrons are sufficiently well localized is by defining Wannier functions. But typically, in strongly correlated systems, Wannier functions and atomic orbitals are almost interchangeable. They're almost the same. That doesn't happen at all in a twisted bilayer. There are a number of papers very early on discussed the issue, and they realized that the situation is very complex. You have these Wannier functions, which have this spinner wheel shape, and finally they seem to overlap. I mean, they are centered at the A, B, and BA regions of the twisted layers, but they seem to overlap at the AA region. Of course, Wannier functions by definition have to be orthogonal, but they coexist, let me put it that way, in the same spatial regions. And that's not trivial, as I said, this is probably the first system in condensed matter physics which has such a complex local description. It is even more complicated because Wannier functions are not uniquely determined. They are not gauge independent. You have to define a gauge in the Brillouin zone in order to describe your Wannier functions. And that usually doesn't matter. But in this case, it does. And moreover, as the continuum model shows, the Valley index is a good index. So whether you are at K or K prime of the original graphene layers is a very good index, but then layers are chiral. They have a finite Chern number, and that implies that you have scars in the distribution of your wave function. You have singularities in the brilliant zone, and that prevents you from having exponentially localized Barnier function unless you cure the situation by going to tight binding and breaking some symmetry. Let me mention, however, that what this basically theorem show from Vanderbilt and Thomhauser shows is that this quantity here are square divergent. So that doesn't imply that you cannot have normalizable Barnier functions. Still, they can be defined, so they are not totally useless. Okay, so now let's move to interactions. As I said, one of the, this is all stuff where we already, from before the experiment, where we already discussed that definitely these twisted bilayers could have a rich phase diagram, but the leading interaction by far, I think by now, there's a general agreement. There are other interactions which are very important, like the electron-phonon interaction, but if you put numbers, the leading interaction is the electrostatic interaction. The reason being, as I mentioned, that the charge distribution is not homogeneous throughout the units. This is a kind of cartoon of what the charge distribution may be. If you put electrons, they will accumulate. That was already known in the AA region. The AB region will be basically neutral, and that creates an electrostatic potential. So as soon as you go away from charge neutrality, you will have an electrostatic potential. You can think of this point where charge accumulates as quantum dots, and then you have some Coulomb energy, which of course here I have left out the dielectric constant. But it has an upper bound of 100 EVs, and even if you put an electric constant of 10, you would still have 10 EV, which is larger than the bandwidth at the magic angle. If you analyze what the role of the intra-atomic Hubbard repulsion, then as the wave functions of the narrow bands are spread out over like 10,000 atoms, the way the electrons in these wave functions interact, you have I mean, each electron has a probability 1/n of sitting in a particular atom. So this is the probability of encountering two electrons on the same side. Then you multiply it by n, and still you have a relatively small number. So intraatomic local interactions are not as important. I will leave out, but I think it's still really worth considering the role of electron-phonon interaction. But as time is limited, I will concentrate now on what happens with the electrostatic interactions in twisted graphene bilayer. This is the first analysis we produced. Niels Wallet from the University of Manchester and myself. As I said, we noticed this question that the charge was inhomogeneous, and then in addition, these systems are strongly correlated, but they are not terribly weird. I mean, they seem to have something which looks like a normal metallic phase, either at high temperatures or at intermediate doping. So the first thing you can do is to check the usual conventional approximations in condensed matter physics. What do they predict? And the first approximation to use is to look at the Hartree approximation, to look at the electrostatic potential, make it self-consistent, and see what's the outcome of this calculation. And as I mentioned, depending which states in the brilliant zone you occupy, you transfer charge from some areas of the unit cell to others. So if you put the electrons at the gamma point, the charge is basically zero at the AA region, and it covers a ring around the AA regions. If your electrons are at the K point, in the brilliant zone, the charge is mostly in the AA region. And as the edges of the brilliant zone have much stronger, larger weight than the center of the brilliant zone, these states are the ones which determine how the Hartree potential looks like. And vice versa. Once the wave functions at the gamma point, they are very much spread out throughout the entire real space unit cell of the Morel area. So they don't feel very much the Hartree potential, the electrostatic potential. On the other hand, the K electrons, they produce the hard-free potential, but in addition, those electrons are sitting where the hard-free potential is highest, so they are shifted. So at the end of the day, McDonald already mentioned that yesterday, you have a significant change in the shape of the bands as you go away from charge neutrality if you take into account the hard-free potential alone. Moreover, the hard-free potential is relatively simple because it's sufficiently smooth within the unit cell so that it's easy to describe by a few cosines, basically. So with one parameter, you describe reasonably well what the how the hard-free potential looks like. But now this effect, the effect that you're changing the very shape of the bands as you change the number of electrons, that immediately tells you that you have a new interaction to deal with. And that, by the way, let me again emphasize, this is a kind of effect not commonly encountered in strongly correlated systems. If you do the same calculation, the same hard-free calculation for the Hubbard model, there's nothing like this. You just have a shift, a rigid shift of the bands, and that's the end of the story. And it fits reasonably well with what is known about the Vanier function, which I have already mentioned. I mean, your Vanier functions have this very special shape. I mean, what I'm trying to say is that in order to change the shape of the band in a localized picture based on Vanier function, what you need to change is the hoppings as function of the number of electrons. This is called electron-assisted hopping, and that is what presumably is happening in twisted bilayer graphene. And it makes sense because the Vanier functions seem to overlap at the AA region. They don't overlap. But if you add an extra potential, this potential very likely will have off-diagonal elements between different Vanier functions. And that's what I mean by electron-assisted hopping that has been discussed in other papers in the literature. Now, this is an extra term which is not included in Hubbard-like models. And let me mention that if nothing else is favored by an interaction term, as Walter Kohn said repeatedly, the only broken symmetry phase which is left at low temperature is superconductivity. That was, sorry, let me mention that that was realized by Jorge Gils way back from UC San Diego, way back in connection with the high TC oxides. He made the case that probably in the oxides, the assisted hopping was at play. He may be right, but definitely if there is a system where assisted hopping has a good chance of playing a big role, is in twisted bilayer graphene. You can justify it by making a simple tight binding model based on what is known about the Vanier functions of graphene, and you just put some hard-free potential which mixes different Vanier functions because they overlap, they seem to overlap at the AA region, and you get like a cartoon of the changes in the band structure I was discussing before. And this is another way, of describing assisted hopping. You have electrons will hop between different orbitals, but if when one of the sides is occupied, the hopping changes, in the case favored by Jorge Gils, because the wave function expanded when it was doubly occupied, then you have this assisted hopping term, which looks like this. So this is an interaction between the hopping and the number of electrons at a given site. If you Fourier transform it, you have an interaction which contains sines and cosines because it involves the hopping. And because of that, this interaction can be either positive, attractive, or negative, repulsive. So it will always favor in different regions of the Brillouin-Son superconductivity. And that was basically the argument of Jorge Gils. By the way, assisted hopping is an old story in graphene. These are relatively old photoemission experiments from Eli Rothenberg's group in Berkeley, where they started bilayer graphene, not twisted or anything, and they found that as function of electron filling, the interlayer hopping changed by about 10%. That's nothing compared to the changes I have presented to you before. but that means that it's not unthinkable to have assisted hopping in graphene-like systems. These are more detailed results where we discuss how the bands are affected by the Hartree potential. This is a case for a realistic dielectric constant. This is the famous narrow band at a magic angle. And this is the change you get when you have either -2 electrons away from neutrality per unit cell or +2 electrons above neutrality. So there are significant change. There is a big change in the total bandwidth, and the band dispersion becomes really weird with a lot of pockets, or it may have a lot of pockets from Hopf singularities and so on. This, by the way, is at least not inconsistent with measurements like the ones Ali Jassani mentioned yesterday about the bandwidth observed in SDM experiments. It's much, much larger than 5 or 10 MeVs. So at least part of this increase in bandwidth can be attributed to the electrostatic potential. And same thing can be said about electronic compressibility measurements done at MIT. They also reported bandwidth much larger than 2, 5, or 10 MeVs for sure. And theoretical work is moving very much in the same direction. There are either tight binding results, this was mentioned by Alan McDonald yesterday, or results obtained for certain fillings. And they all tend to show that the electrostatic interaction alone, described with different types of approximations, are enough to give a relatively broad band. By the way, other things like heterostrains, for instance, can do the same. But the Hartree approximation is an interaction where all electrons talk to all the other electrons. There is no flavor, there's no valley or spin dependence. So it will never explain the insulating phases where presumably you have broken some symmetry. The Hartree approximation can give rise to broken symmetry states, but it's very unlikely. For that, you need to expand your your set of tools and include the exchange term. You have to do at least a full Hartree-Fock analysis, and the Hartree-Fock approximation in graphene has a long story because the exchange term is also responsible for the most striking effect of interactions in single-layer graphene, which is the renormalization of the Fermi velocity, which can be predicted. It's the same renormalization you have in quantum electrodynamics, only in 2 dimensions, and with a much stronger coupling constant, which is no longer 1/137. And in a twisted bilayer, the effective coupling constant is not 4 to 2 or 3 like in a graphene monolayer, it's more like 10 to the 2. So definitely it's worth looking at what happens to the exchange term. It's worth doing a full Fock calculation. And then you can compare broken symmetry phases. The study of broken symmetry phases is tricky because you get what you put in some way. You need to make a guess about what symmetry you want to break. You cannot study all the very many symmetries which possibly can break in graphene. There is one which is simple and which is typical of half filling and which inherits the effects of the Fermi velocity renormalization I just mentioned. It's a phase which C2 symmetry is broken, which basically means that electrons tend to go to one sublattice and not to the other. So you break inversion symmetry, you fill up more one sublattice than the other, and you open the gap. And that is the extreme case of the Fermi velocity renormalization in graphene. The Hartree-Fock approximation tends to exaggerate these effects, so probably these results, which are consistent with other calculations, by the way, are a bit of an upper range or an upper limit of what to expect. And the other kind of broken symmetry phases, you can expect simple broken symmetry phases. You can expect are polarized phases either in the spin or the valley degree of freedom. Here there are different phases. In this phase, you have two slightly more occupied bands than the other two. I mean, you have 8 flat bands divided in a valence and a conduction band for each spin and valley. And here we assume that 2 sets of bands for some values of the spin and valley are more occupied or have more electrons than the others. This is the same thing, but with 1 + 3 and 3 + 1. These phases also can be found, and definitely you can find self-consistent solutions which are stable at many fillings, not just at integer fillings. And the question of which phase is more stable than the others, that's really tricky because the energy differences are tiny, are of the order of millivolts per real space unit cell, which contains 10,000 atoms. So one cannot take these calculations at face value. They strongly depend on the parameters you are using, but at least they give you a clue of what to expect. By the way, let me mention that in any case, if you look at the bands you get, there are tiny gaps, or in the case of half filling where there's no hard treatment, there is a relatively large gap due solely to the exchange term, to the Fock term I have just discussed. Away from half filling, still the hard tree part of the electrostatic interaction dominates. And there's a good reason for it. The hard tree term, the electrostatic interaction, couples every electron with every other electron, while the Fock term is something restricted to each electron flavor. So it only couples spin up valley K electrons to spin up valley K electrons, and so on. So there's a factor of 4 which makes the exchange term smaller. Actually, you could even make a 1/n expansion in the language of statistical mechanics or quantum chromodynamics, where actually ND3 is the number of quarks. And then you can justify in a more rigorous way what I was telling you before, the relevance of the hard tree interaction. At the very least, it's 4 times larger than the next interesting interaction, which is the exchange interaction. And this is a kind of possible phase diagram. As I said, we found slightly more stable phases than a simple metallic phase at all fillings. However, these phases, unless this is actually not the best phase for the parameter we have used, the phase which opens a gap at half filling. All the other phases tend to be gapless. There are always small pockets somewhere, and that's why this is the density of states at the chemical potential. Even very near integer fillings, the density of states never vanishes. So these phases can be considered bad metals, something like that. But they are not full insulators, at least at this level of approximation. But it's interesting because if you have many different phases and you have to move from one to the other, that has been already discussed in the literature, as I will discuss, then you have to jump, for instance, between this phase is stable for +2 electrons in the unit cell. This phase is stable for +1 electron in the unit cell. So at some point you have to jump from this to that, or from this to that. If you go from 2 to 3, you have to jump from here to here. And this is the kind of simplified picture one usually uses, called the Maxwell construction. So typical, I mean, you have this phase, you have this phase, as far this is the density. This phase has a minimum near 2 electrons per unit cell. This phase has a minimum near 3 electrons per unit cell. But you will never get to this point or this point. It's always easier to make a combination of this phase and this phase. You will get a lower energy, and that is called electronic phase separation, and that's well known. And actually, in that respect, these systems resemble some of the well-known strongly correlated systems, namely the double exchange systems and the pyrophores, which are magnetic systems with a very complex magnetic phase diagram with many possible magnetic orientations and a lot of electronic phase separation in between. Electronic phase separation is never a complete process because you have to find the Coulomb energy. You have to accumulate, make charge paddle somewhere, and that causes you Coulomb energy. So it's actually to study electronic phase separation in the presence of the Coulomb interaction, as it always happens. It's really a complicated system, but the typical picture you have is this Maxwell construction. And this is actually, and this is also consistent with something like that Danny mentioned yesterday, this cascade picture of different phases appearing as you change the feeling of the system. At least this is not completely inconsistent. Which are the phases involved in these phases, in these phase diagrams? I am not sure, because I have shown you a possible scenario based on spin and valley polarized phases, but as I said, everything is highly sensitive to the parameters we use. Okay, but now I'm going to move on. Let me discuss now, because twisted bilayer graphene nowadays is not the only system, graphene-like system with flat bands, what people have reported insulating behavior or superconductivity. One of them is a bilayer on a substrate. These are two papers still, I think, unpublished, but they reported superconductivity on bilayer on hexagonal boron nitride. There is a more extensive work on an ABC trilayer on a substrate. There are reports of superconductivity, insulating behavior, and so on. And there are also reports of either insulating behavior or superconductivity on a graphene bilayer twisted with respect to another graphene bilayer, the so-called bi-bi system. So we have looked to what happens in these three classes of systems. What does at least the electrostatic interactions do in these systems? These are non-interacting band structure calculations, which are in reasonable agreement with what people have estimated in the papers I have shown to you before. So there is an extra knob you can tune, which is the bias between the layers, and depending on the bias, you have narrower or wider bands. We shows the narrowest bands you could achieve, and then we turn on the interactions, and so these are self-consistent solutions. This is the density. The density is very different from a twisted bilayer for this particular case, and the bands don't change much, don't change at all. For the ABC trilayer, similar thing. These are the bands as function of bias. Before one turns on the interaction, then we go to this case where you have the flattest band possible. You turn on the interactions, again, you have funny charge distribution, and the changes of the bands for realistic values of the dielectric constant and everything are very much unlike the changes of the bands you have in twisted bilayer. However, let me mention that in all these cases, the topology of these bands is complex. It's even more complex than in twisted bilayers if you look at Chern numbers and things like that. And this is the last case, twisted bilayer graphene on bilayer graphene. Again, depending on the bias, zero bias, you have flat bands. If you increase the bias, one of the bands may get flatter, the other not. Again, these are non-interacting calculations in good agreement with previous calculations. And again, the HAR3 effect, the electrostatic potential, it changes the bands a little bit more than in the previous cases. But you don't see a drastic change in the shape as in a twisted bilayer. So these bands look, that's the point, look significantly, I mean, the behavior of these bands when you turn on the electrostatic potential, by the way, which is more complex because, as I mentioned, the charge distribution is more complex than in a twisted bilayer, but you can do a decent self-consistent calculation, but the bands move almost rigidly, which is what I said at the beginning. That's the way it happens in most strongly correlated systems up to date, until twisted bilayer graphene came into the picture. Let me finish by explaining the last part I wanted to tell you about. Is about graphene on a substrate. These are all results on that topic. But graphene on a substrate, the moires you had with graphene on boron nitride, when graphene is aligned with boron nitride, they were a big industry during quite a long time. It's very interesting to notice this question. If you put if you align graphene with boron nitride, you break down reversal symmetry, the two sublattices in graphene become inequivalent, and then you can open a gap, which was something which proved until this paper to be very difficult to achieve in graphene, because not even the exchange term only renormalized the Fermi velocity, but didn't open a gap. Theoretically, the issue is well understood, and you can make fits. I mean, you just need basically 6 parameters for a sufficiently large moires, and these moires are similar to the twisted bilayer graphene moires. They have 11, 15 nanometers, no, 12 nanometers of unit length, with 5 parameters. One parameter define, 2 parameters define the scalar potential, a kind of periodic mass term, a constant mass term, and a gauge field. With that, you can describe this interesting band structure. So you have mini bands with gaps and new Dirac points and so on. And that eventually got very well understood during the early between 2013 and 2016, let me put it that way. So, but it turns out, and this is the last thing I wanted to mention, that in the case of twisted bilayer graphene on hexagonal boron nitride, you have to deal with 2 moires. One moire is the moire created by the 2 graphene layers twisted with respect to each other, and then you can look at the lower. Let's suppose that you only consider the possible alignment of one of the 2 sides, one of the HBN layers with respect to one of the 2 layers of the twisted graphene bilayer. So you have 2 moires. If the graphene layer is perfectly aligned with HBN, the 2 moires are at right angles, and they are almost a quasi-crystal. There's a nice paper by Mikito Koshino about quasi-crystals you can create with twisted bilayers. This is a similar situation. And I mean, the problem becomes really complex because the 2 moires are they are as different as they can. But you can change little by little the angle between hexagonal boron. You keep the magic angle between the 2 graphene layers, but you can change little by little the angle between one of the graphene layers and HBN. And it turns out that, and then you are changing the other moire. And it turns out that there is an angle, which is for the parameter we have used, is about 0.5 degrees, so it's very small, where the 2 moires coincide. So then you can do a lot of calculations. Then the problem becomes quite tractable. And these are the results. So this is the situation I am mentioning here. The 3 layers are put one on top of the other at this metamagic angle where the 2 moires coincide, and you see with your naked eye that that's the case, that you can see a nice global moire built from out of the 3 layers. And this is the same situation for different angles. This is this situation. These are the 2 Brillouin zones sitting one on top of the other. The red Brillouin zone is the Brillouin zone defined by the moire formed between HBN and one of the graphene layers, and the black Brillouin zone is the Brillouin zone coming from the moire between the 2 twisted graphene layers. That's why the black Brillouin zone is always the same, because the twist angle is kept fixed. And as you change this angle, you make the moire unit cell in real space between HBN and graphene smaller and smaller, and the Brillouin zone becomes larger. This is the quasi-crystal situation, but you can still do calculations. You need to make many copies of your twisted bilayer in order to get a good convergence of the two moires and so on. But the crucial thing, this is the flat band in this situation where you have an angle of 2 degrees between HBN and graphene, in which case basically the graphene becomes decoupled from HBN and you have a flat band. But notice, and this is the case where you can do pretty good calculations because the two moires coincide. But notice how very quickly the flat band gets disintegrated, basically, disappears. And it's coming because not only you have an average gap, which is this mass I discussed before in connection with the usual moires, there are a lot of non-homogeneous gauge fields and scalar fields coming into the picture. And the numbers you have to include are typically 10, 20 MeVs. I mean, that's the effect of these non-homogeneous potentials induced by hexagonal boron nitride when it's aligned with graphene. And of course, they are larger than the bandwidth of the bands at the magical angle. Here, there are no interactions, but they are enough to make the bands disappear. So there is a really big change, and I think these calculations are quite reliable. There's a very big change as soon as you align twisted bilayer graphene and boron nitride. So that's the general idea. Okay, so this is work in progress. There will be a poster. This is a collaboration with Wuhan University and us on flat bands in two-dimensional light chalcogenetics. Is related to the first topic Alan McDonald mentioned there. Another topic we're looking at, I mean, as I said, the Wannier functions have the not very satisfactory feature that they're not gauge invariant, they are not uniquely determined. And we thought that maybe another way of looking about the complexity of the electronic structure of these systems is to look at the quantum metric, which is a gauge invariant property, and we're looking at it. These are some preliminary results, but we still don't have very conclusive results. And that's it. These are the topics I have discussed. First, I have emphasized the relevance of the electrostatic interactions. Second, I have discussed how the electrostatic interactions give rise to new features not typically observed in strongly correlated systems. And third, I have discussed how these features, which are very prevalent in twisted bilayer graphene, don't seem to play the same role in other narrow bands made with graphene stacks. ABC trilayers and so on. And this is my collaborators, Nils Wallet, Tomás Osea, Pierre Pantaleon, and Roy Brown. Thank you.
Thanks a lot, Paco, for this very nice talk. I see there are a few questions, and in particular from Christian. So I know that you're with a group of people at ICFO. So maybe you can ask now.
Hello.
Christian,
yes.
Can you hear us? Yeah.
Yes. So first of all, thank you for the very insightful talk. It was really nice. And I have a question about the plot you have shown, where we see that increasing the HAR3 potential changes the band structure of twisted bilayer graphene. And you have shown 3 plots for 3 different magnitudes of HAR3 potential. And I'm wondering to what carrier density this HAR3 potential magnitudes correspond to.
Good, yeah, good question. Okay, let me find the results again. Okay, so the best case, okay, first of all, we were very intrigued by these results at the very beginning, Nils Wallet and I, and we looked at situations where the changes were not terribly dramatic. We didn't want to deviate from orthodoxy too much. So these are situations with a lot of screening, and nevertheless you see significant changes. This is more realistic. This is a more realistic screening constant. This is a magic angle. So these are the narrow bands as coming out from a continuum calculation. And this is what you get if you have +2 electrons per unit cell. And here is what you get if you have -2 electrons per unit cell. And these are the bands, and this is the density of states.
So this is half filling.
Half, I would call half filling. The neutrality point is here. because there's no hard treatment. So this is away from the neutrality point, but you're right, it's half filling if you describe half filling as 2 electrons per unit cell out of a possible maximum number of 4.
Okay, so this is already quite significant in the Fermi level in the flat band.
Yeah. But as I said, these results now are quite consistent and have been reproduced and so on.
Okay, great, thank you.
Thanks. I see there is another question from Pablo. Pablo, can you speak now?
Hi, Paco. Can you hear me?
Yes, perfectly.
Yeah, I wanted to ask you about the alignment of the HBN to the magic angle graphene. As you know, most experimentalists, we have 2 HBN flakes, one on top and one on the bottom. So in principle, you have 3 mores. Have you looked at what is the effect of the third more?
No, the complexity, I mean, here we're solving a problem which goes like the square of the 2 mores. And the problem you're defining, which will go like the cube of 1 more. And that, up to, for us, is out of the question right now, but it will be interesting to do it for sure.
Thank you.
I see there is another question from Shalal Ilani. Shalal, can you hear us? Yeah.
Yes. Hi, Paco. I wanted to ask about the compressibility and the Hartree effect. You showed that the Hartree effects can be quite substantial. I wanted to know if you can estimate or even calculate quantitatively how they modify the compressibility as function of density.
Yes, good point. Okay. It's complicated because the compressibility, if you add the Hartree term, is not the same as the density of states, which is plotted here. The compressibility is the second derivative of this curve. And as I said, the differences between different phases and everything is really tiny. We can get an average with the main part. We can leave out maybe the exchange term, keep only the Hartree effect and do it properly. Yeah, so it's a good suggestion. We can do it. But only for the Hartree part. How they insulate, what is the role of the insulating phases to get reliable numbers for the compressibility? Now, maybe it's doable, but I'm not very sure right now. But thanks for the suggestion.
Thanks. Is there any other question? Well, then maybe I could ask one meanwhile. I was reading this paper from the group of Rubio about bilayer HBN, and what they were showing basically is that there is no magic angle. Like the flat bands that appear at low angle, the width will progress monotonically with the angle. And I was kind of wondering what is the key ingredient that in HBN and in graphene would make then therefore you have like this. This magic angle, this special angle. Like, what is the
main difference is that you don't have a Dirac point. You don't have to deal with 2 bands per layer. You have just a parabolic band per layer because you're looking either at the top of the valence band or the bottom of the conduction band, and it's more like Schrödinger electrons moving in an effective potential. The difficulty, which makes twisted bilayer graphene really interesting and special, is that you cannot do it. There's no gap, so you have the spin and value degree of freedom. You have 2 bands. No? You have the superlative degree of freedom. That's the proper way of putting it. You have the superlative degree of freedom, which is unavoidable. In HBN, the valence band lives mostly in one sublattice and the conduction band lives mostly in the other sublattice, and that really simplifies things.
Okay. I see there is a question from Evgeny Redekop. Evgeny, you can speak now.
Do you hear me?
Yep.
Okay, thank you. So thank you for your wonderful talk, and I wanted to ask you about these Dirac points. So if we have, for example, Kagome lattice, so which exhibits Dirac cones, then if we twist 2 layers of these Kagome lattices, we could have some more patterns with flat bands. Am I right?
Absolutely not. That will be a very interesting problem. I didn't think about that, but I agree with you. That's by no means trivial.
Okay, thank you very much. Thank you.
Okay, I wonder if there is any other question. Don't be shy. Also, there will be the poster session, and Paco will be around in this second time, that second platform. The link will be sent or has been sent already. But if there is no more question, then I think we could thank our speaker again, and therefore move on to the last session of today, which is this poster session. So thanks a lot. We zoom out now and see you in a bit. Thanks again, Paco.
Thank you.
Okay, thank you very much. Thank you, Paco. We're gonna finish the meeting here and we'll see you in the poster pitch session. Bye-bye.